Okay, so I'm going to continue with a few more models. I'm going to start with a simple a simple disassembly model. So, and this is actually something which more complex versions of this are actually part of a thesis I'm currently advising for a maintenance facility for helicopters. And this is just kind of this would be a first cut at a front end of that. So the first thing they need to do is basically take them apart. Okay, so we're gonna kind of look at that. And then we're going to talk about transient entities. And this is kind of building on what we talked about for that simple version of the reneging situation, where if we want to get more information, then we actually need to start representing our customers with a little bit more expressiveness. And that's where this idea of transient entities comes in. And then we're going to apply that again to yet another basic multiple server queue model. And except it's going to use these entities. And then in order to drive it, we're going to need an arrival process that actually produces these things. So as we'll see, these are going to actually be objects that represent the individual customers. As we said, our models up to now have not really captured the individual customers, but have just been counting things. And actually this disassembly model is also just going to be a count. So what's this one about? Well, the idea is that the parts are going to arrive to a queue, as we're familiar with what that's about. But now what is the service consist of? Well, what the service is going to consist of is first disassembling them. And we're going to say that these parts have two components, well, and I'm going to call them parts two, or component A, component part A and part B. So a part has one A and one B. And what we're going to do is we're going to separate them or disassemble them. And then once they're separated, we're just going to have them inspected, or the inspection could be some kind of processing, or we're going to call it inspection. And the idea is that those inspectors are actually different than the workers who are disassembling. So we have two specialized workers. So the workers who disassemble only disassemble, and the workers who inspect only inspect. Now, the thing is that the same set of workers now are dealing with two different parts. So, and if an inspector is going to be in a situation where all of a sudden, when a part gets disassembled into its two components A and B, now the model needs to be explicit about what happens. And so a worker, if there's only one worker available, there are now two tasks to perform. And they both arrived at exactly the same time. So what do? Well, this is where the model needs to add an additional logic, some additional logic. So what is the worker supposed to do? Now, what we're going to start with is the worker is going to just prefer to inspect A over B. So if there's one worker and both an A and a B show up, which they will at the same time, they're going to inspect the A, and then they're going to inspect the B if nothing else shows up. However, the rule that we're going to have is that they always prefer A over B. So if an A and a B show up, then they inspect A, but while they're inspecting that, if another A and a B show up, they're going to also do the A. Okay, so so when the second type of worker finishes inspecting, then they will always, quote, prefer to inspect a component of type A over type B. Now that's the rule we're going to have. And then at some point, we're going to have to kind of look at that rule. But that's where we'll start. But the important thing is to recognize that we need a rule there. We need something that says what they can do. And if we're not careful in our event graph, we might have them doing both of them. So we just need to be a little careful. All right, so let's start modeling this. Again, this should look very familiar. So we have two types of workers. We have the disassembly workers and the inspection workers. Okay, so that is fairly straightforward. Okay, so for the disassembly workers, we have the disassembly times. So that's how long, again, in the model, in the implementation, that's gonna be a random variable. But now we have different inspection times for A and B. All right, now, so let's look at state variables that we have. Well, now, why did we switch from S to W? W for worker, I guess. I don't know. Doesn't matter. What we label these things are less important than how they operate. Okay, so we'll call W0. Those are going to be the number of available disassembly workers, initially going to be K0. And W1 is going to be the number of available inspection workers, again, initially K1. Okay, so now we have three queues, though. We have the basic parts queue before disassembly. Now we have how many disassembled A components are waiting to be inspected. And we have the number of disassembled B components waiting to be inspected. And they're all initially 0. So now, again, our model has three different queues, and we need to keep track of all that. So again, these are the additional assumptions that the inspectors are going to inspect A over B if given a choice. We're not going to worry about the reassembly operation. I mean, obviously, in the student who's modeling the helicopter maintenance, at some point they need to be put back together. So, but for this component, we're not going to model that. And in fact, in that model, the disassembly and the reassembly operations were actually modeled using different components. Now that the model that that student is using, the components are much more complex than what we're dealing with here. And then the arrival of the parts, again, they're going to be modeled with another component. And as you might guess, an arrival process is going to be doing that. Okay, so rather than, okay, here I'm just going to show you the whole event graph because it is kind of spaghetti-like. But if we parse it out, we can kind of see that there are some common patterns here. So first, actually, let's just sort of disregard everything that's below this red line here, and just look at the top here. Okay, we have our parts waiting to be disassembled. This should look very familiar. When a part arrives, if there's an available worker to disassemble it, we'll schedule a start disassembly, which decrements the number in the queue of the parts, decrements the number of available workers. And then when we end that, we now have another available disassembly worker. And if there's another part waiting to be disassembled, then we'll schedule that. Okay, so this piece, so even though at first glance the model may look a little overwhelming, If we just focus on this piece, we see that there are a lot of, again, just kind of ignoring this for a second, we see that there's a common pattern that we're used to here. Oh, and then of course we always need to have the run. The run we can always put down. So none in the part queue, none in the A and B queue. The worker 0 is the disassembly worker is the number that we have, and the inspection worker is the number we have there. Okay, so again, this piece of the model is fairly straightforward. Now, let's look at what happens. When we finish disassembling, it's, what basically happens? Well, what happens is we now have our two components, our A and B component. And so once they're finished disassembling, we're going to assume that it just in no time, we now have these two things available. And so that means that each of the queues are going to be incremented. So this is something a little different. We have two queues. Now all of a sudden we got two guys showing up at once. So here is where we have to implement that rule. So if there is, when that happens, if there is a inspection, if there's at least one inspection worker available, we can start inspecting A. And if there are at least two available, then we can also start inspecting a B. So in other words, if there's only one inspector available, then we start inspecting A, and then this fails, and we have to wait until sometime later. If there are two or more available, then this condition says, okay, we can start inspecting A, but then we have another worker available and they can start inspecting B. So both of these could be scheduled at exactly the same time if we have enough workers. Now if we just kind of focus only, let's just focus only on this piece right here. So when we start inspecting A, we now have one fewer worker for inspection. We have one less in the queue. And then we schedule the inspection time with a delay of how long it takes to inspect the part A. And then when we finish, okay, well, let's, we'll do the finishing in just a second because it's fairly complicated.
Arnie, I have a question, just one step back. How do you, if W1 is the if statement for both inspect A and inspect B, maybe I missed it. How do you say which scheduler is first? Because if it's W, I mean, I guess it would just wash out.
Yeah, in this case, it doesn't really matter.
Okay, so if it was 2, then it takes it down to 1 and it's scheduled at the same time. Okay.
Yeah,
okay.
Yeah, exactly. Yeah.
Right, yeah.
But great. I mean, I'm glad that you raised that. So again, let's just, it helps to walk through, let's put a number in. So let's say that there are W1 is equal to 2 when this event occurs. Okay, so 2 is bigger than 0, so it'll schedule this start inspect A. 2 is also bigger than 1, so it'll schedule start inspect B. Now, does it matter which order that happens? Well, let's take a look. So start inspect B will occur. Now W goes from 2 to 1 and then schedules this after a delay. Again, this is going to be in the future. And then start inspect A event will occur next because they were scheduled at the same time. And so now W1 goes from 1 to 0 and then QA, et cetera. So in this particular case, even though these events are occurring at exactly the same time, the order that these state transitions occur doesn't matter. And you should convince yourself that that's the case. In other words, these conditions guarantee that at the end of this, W1 will go down by 2, one here and one here. But great, great question. Okay, so and again, even though it kind of looks messy, if we focus on individual pieces, we can see these same patterns here. Okay, but here's where things start to differ a little bit, and that's why I keep doing that. Okay, so here let's look at end inspect A. Okay, so we now have an available worker. So if what this says is, because we prefer to inspect an A, that says if there's an A waiting, we'll inspect that. Okay, but here's where things get really a little dicey. If we want to maintain that same rule, we have to apply the same scheduling edge if we end inspect on a B. In other words, even though we just finished a B, if there's an A waiting now, we need to do that. Because that's the rule. That's the rule that we have. Now, is that a good rule? Not necessarily, but it's the rule we have. And if you believe that all policies in places like this are good ones, then I have a bridge I might be interested in you buying. Okay, so I'm not saying that this is a great rule. In fact, it's as we'll see when I'm going to implement this and run it, and we'll see what an issue is. All right. So again, however, what do we do if there's no available part A, but there's an available part B? Then we can schedule an inspection on B. And that's true whether we finished inspecting on an A or we finished inspecting on a B. This is where you might be tempted to only have QB bigger than 0. So let's look at what would happen if we just didn't have this condition. So let's say that when we finished inspecting on a B, W1, now right before that, we didn't have any available. So W1 was equal to 0. Now W1 is equal to 1. Okay, look at what happens if we don't have this first part of the condition. We have, let's say that there are parts A and part B in the queue. So what will this do? This will schedule a start inspection on A, and it will schedule a start inspecting on B. But if that happens, then regardless of the order that these happen, because we now have 2 decrements of W1, if W1 is 1 when this is scheduled, it will now be -1 when these 2 events are finished. In other words, what we're saying, what this is saying, if we leave this condition out, is that this guy can inspect both A and B at the same time. And what we're saying is that is not physically possible. Okay, so in other words, he can only, or she can only inspect a B if there's no A available and there's a B available. And this condition will prevent them from doing both. Okay, so we see that this event graph, when you first saw it, probably looked intimidating, or I don't know if this it looked complex, it looked confusing. But if we kind of parsed it out, it hopefully became less confusing. Everything in here is dictated by the logic of what we're modeling, not by what we're kind of used to. Okay, now there's one little thing that that this did here. I see some things in the chat. Well, yeah, okay, well, yeah, okay. I like the comments in the chat, but we're going to pretend that that we're operating according to somewhat reasonable rules. You can only do one thing at a time. Actually, studies have shown that this whole multitasking thing is actually a myth. I mean, but that's neither here nor there. Right? Something that I did though that is, and this was somewhat deliberate. Notice that instead of an arrival event, I had something called part arrival. And you know, that's a good name for this because these are parts that are arriving. However, what that means is that our arrival event, I'll just call it A. So our arrival event, if we want to try to drive it like this, is not going to work. See, so now why? Now the plain arrival event didn't work for when we had an argument on the arrival. And so and there's no way we can make that work without producing another event. But here, the part arrival, the part arrival event has no arguments. And the only thing that's preventing our arrival event from triggering the part arrival is the fact that they have different names. And so what to do about that? Well, that's where this concept called adapter comes in. And the adapter, it's in the reading, so you can kind of look at that. But here's what an adapter does. So the signal for this is like a double-edged listener thing, and together with two names. So what this does, well, you all know what an adapter is, right? I mean, if you have an adapter from one type of connector to another, all it does is it takes one thing and it turns it into another. So for example, when I got the earbuds for my iPhone and I wanted to use it for, and again, I'm old fashioned, so this is still with the cord. I wanted to use it in my laptop, which has an 1/8 of an inch input. So I just got an adapter, and an adapter went from the little, Thunderbolt or whatever that thing is into an 1/8 of an inch thing. So it took one type of connector and it turned it into another. And that's what an adapter does here. So an adapter will take an arrival event in the arrival process. And as far as the arrival process goes, this arrival event is what happens. But then when it dispatches it via an adapter, this changes it into a part arrival. And that allows us to use an arrival process to drive our simple assembly. Now, okay, so I want to implement this. So let's take a look at that. Maybe I should share the whole desktop to do that. And no, that's related to. Simple disassembly. There it is. Okay. And I can see. Okay, so here are our parameters. So the number of disassembly workers, the number of inspection workers, the disassembly time generator, the part A inspection generator, the part B inspection generator. And then here are our state variables: the number of available disassembly workers, the number of available inspection workers, the number of parts in the queue, the number of part A in queue, and number of part B in queue. Okay, so So what's kind of the key here? Again, our reset method is what initializes our state variables, and we just have, again, for these, again, notice that the run event does not schedule any events. So just watch out for that. Okay, so the part arrival, fairly straightforward, start disassembly. So here at the end disassembly, this is where things start to differ a little bit from what we may be used to. So let's take a look at that. Okay, so this first part is the, now we have an available disassembly worker. That's this right here. But now we are adding to the queue. So the number of part A and Q we increment, number of part B and we increment. Again, that's these two state transitions. And then now the thing about event graph if statements is because each one is on a different different scheduling edge, there's a tendency to not use the else. I mean, and so I discourage the use of an else in this. Now, sometimes it's logically okay, but sometimes it's not. So for example, if I were to say, if Q is bigger than 0, then do this, else if W1 bigger than 0, that would be incorrect because the two are actually independent. What I prefer to do is just literally translate. So literally translate. If Q is bigger than 0, start disassembly. If the number of parts in the queue is bigger than 0, I schedule a start disassembly. And now I didn't have the high on the event graph, but again, typically for an event like this, we do want it to have a high priority. Again, keeping in mind that the priority for an event does not have anything to do with whether the inspection worker prefers A or B. I mean, you could think of that as maybe priority, but I would avoid thinking of that as a priority. Think of it instead as a preference. And then notice that, okay, the conditions, if it's bigger than 0, I'll start inspect A. If it's bigger than 1, I'll start inspect B. And then, okay, that's fairly straightforward. So let's look at the end inspect A and how we do that. Again, if the number of part A and Q is bigger than 0, we're going to do another inspection. If the number of parts A and Q is 0 and the number of part B and Q is bigger than 0, then we'll schedule a start inspect B.
Arnie, would that cause an issue because you'd be decrementing it down by 1 and then it no longer be greater than 1 in the part in inspectors up above what you just went through?
Well, yeah, you remember that a wait delay statement does not actually call it. A wait delay statement simply puts it on the event list.
Oh, okay.
So that's an important thing to remember. So yes, if I were directly calling these events inside another event, then that would be an issue. But since I'm not invoking those because the decrement in these cases has not occurred yet. I've just put this on the event list. The decrement doesn't occur until this event occurs and this event occurs. So, and because they happen sequentially and separately, then it's actually okay. In other words, well, and in this particular case, only one of these two is going to execute. So here I could have had an else instead of this.
I meant the function above that.
Yeah.
If you go up for end disassembly.
This one here. This one. Yeah. See, great point. Yeah. So by putting that, when I put these on the event list, so let's say both of these are true. then the only way these can be true is if the number of available inspection workers is at least 2. And then when they occur, even if they're going to occur at 0 time, so regardless of which one happens next, okay, this will decrement it. So let's say A happens first. This will decrement it. Now it goes for, oops, here, it'll go from 2 to 1. And then this will happen, and then it'll go from 1 to 0, if that's the case. Okay, so and then likewise with an end inspect B, again, notice that I have this as well. So so actually these 2 events, the end inspect A and end inspect B, in this particular case actually could be combined into one event in this particular case. I left them at 2 because in part because of what's going to happen when we run it. So let me where the heck. There it is. Okay. So let me everything in the here's my main method. So I have an arrival process that I'm going to use to drive this. I have I put uniform times for the disassembly, the part A inspection, and part B inspection. Okay, now I instantiate it. So here this is the new thing right here. So here's where I do an adapt. If I just do a sim event listener, it's not going to work because my simple disassembly model requires a part arrival event per the event graph. But my arrival process is producing an arrival event. And so in situations like that, where I have an event that would be perfect because the signature matches, the only thing that doesn't match is the name. So the adapter, I work the adapter like this. First, its arguments are, this is the scheduled event, and this is the heard event. And then the method is connect. I just connect them. So I connect the arrival process to the simple disassembly. And so what's going to happen is that whenever an arrival event occurs, it's going to schedule a part arrival. And let's see. So let's just stop at so let's just kind of see what we have going on here. So again, we confirm. This is always important because I was just doing a model the other day and I had forgotten to set one of the parameters, and I only caught it because I did a print line here and recognized that it was I think it was one of the generators. It came up null, so I knew to stop and say, okay, nothing more is going to happen. Okay, so here are our run events that are happening. Here's the run event for the simple disassembly. Again, I want to verify that the state transitions are correct, the initial values. Okay, so here's the arrival. Now, the adapter kind of hides some stuff under the hood. So under the hood, as far as the event graph is concerned, it's the arrival event that's actually happened. But notice this, that when the arrival event, and this was from the arrival process, when that occurred, something was happening in the simple disassembly. The number of parts in the queue was incremented by 1, and it scheduled a start disassembly. Okay, so you see that. So that's the adapter at work. That's sort of the main point of this. Okay, so and then the rest is fairly straightforward. And so let's run it. My latest favorite processing time is 100,000. So Y, it's got lots of zeros. Okay, so so I run it, and I get the average number in the part queue, the average number of the part A queue, the average number in part B queue, and the utilization of our two workers, types of workers. So I had 2 disassembly workers and 2 inspection workers. And now let's take a look at this and sort of see what the heck is going on. First, notice that the time for inspection of Bs is actually less, quite a bit less than those for As. And these are uniform distributions, but the distribution of the part As are significantly less than that of part B on the average. But let's look at what's happening with the Q. See, the part A, okay, the regular part Q, 7 something, you know, that's not too bad, especially in, you know, running it for a long time. The part A Q, that's really good. But look at the part B Q, it's like 28. Okay, so obviously, what is happening here? What's happening is that our policy of preferring the A's to the B's is screwing the B's. And furthermore, that's also screwing things up downstream as well, because when we if we have to say reassemble these, and to get a full part, I need a part A and a part B to get a full part. If this is what's going on, there are going to be situations where I have a ton of part A's and not many part B's. Okay, so what that means is that our basic rule is kind of screwing us over. And now, that wouldn't necessarily have been the case, but when we ran the model, it told us that was happening. How? Because our part AQ was very small and our part BQ was huge. Now, actually, are these utilizations of over 0.9, those are also a little concerning, but that's sort of a different matter. Okay, so what that means is that maybe an alternate rule is in effect. Okay, so what might mitigate this? And again, I'm running way out of time here. So, but okay, so let's look at an alternate rule, and that's let's look at the rule that we switch if possible. In other words, if I've just finished an A, then I want to do a B next. So that maybe that should be a little more equitable. So how can I do that? Well, if I just look at the start inspect and end inspect events, and I don't have to look at the whole thing, but if I just look at this, how could I implement that? So that means that when I end inspect an A, then if a Q is big, if there's a part B available, I will inspect that. I'll switch to that. And of course, I don't want to sit there idle. So if there aren't any B's and there's an A, I'll do that. Likewise, if I finish on a B, then I want to do an A, if possible. And if it's not possible, then I'll do that. So that's an alternate rule, another rule that I could implement. You know, I haven't done that, and I don't have the time here to do that. Actually, I think I will show how to do that by tomorrow's class. Here's another possible rule. Another rule might be I choose the larger queue. I have 2 queues, and even with the switching thing, that may or may not balance things out depending on how things go, depending on how many work. If I have an odd number of workers, then things might get a little unbalanced. But another alternate rule is that if I have more of one type weighting than the other, then I want to choose the larger one. So how would I implement that in the event graph? Okay, so I finish inspecting an A. And if now here I need to figure out what happens if they're exactly equal. So what I've the extra tiebreaker rule is if they're equal, I'll stay with what I'm just doing because it doesn't really matter. Another alternative rule is I could just flip a coin. But if I've just done an A, I'll do another A if they're exactly the same. But if the Q for parts A is bigger than or equal to that of part B, then I'll inspect that. On the other hand, if the B Q is bigger, I'll inspect a B. And similarly for ending inspecting a B. If there's a B available and the Q is bigger than or equal to the other one, then I want to start inspecting a B. On the other hand, if QA is bigger than QB, I'll start inspecting an A. Now, why? Here's the thing, just to watch out for edge conditions. An edge condition is if both Qs are 0. In other words, if both Qs are 0, then I don't want to do anything. Okay, so if these Qs, if both of these are 0, this will be true, but this will be false. And this will be false because because 0 is not bigger than 0. And 0 is not bigger than 0 here. So that's just an edge condition you need to watch for.